Floor is yours. Thank you.
Thank you, Anna, and thank you, the organizers very much for inviting me to give this presentation, for organizing this beautiful conference. So when I wrote my abstract, I was thinking about talking about tuning interactions in rubidium-strontium mixtures by reduced dimensions and Feshbach resonances. And over the last 2 weeks, we had some very interesting hints on perhaps having obtained rubidium-strontium molecules in the lab. So let's see. Let's start at the beginning. We use rubidium, an alkali element, and strontium, an alkaline earth. In rubidium, we have one broad laser cooling transition. In strontium, we also have a broad blue one, but then also narrow intercombination lines. And it's very useful to have a 7 kilohertz line of transition that's great for laser cooling to below a microkelvin. We also have an optical clock transition here in rubidium. We do have a microwave clock transition, which is very useful for calibrating magnetic fields. Now, let's discuss a few properties of this mixture that we will make use of. If you use a dipole trap around 1064 nanometers, you will trap rubidium 3 times more strongly than strontium. And if you use, say, an optical lattice at 532 nanometers, the bright antinodes will be attractive for strontium but repulsive for rubidium. So in this situation, you could make a patterned loading of rubidium and strontium this way, where the spacing between these species would just be half of the lattice spacing, so 133 nanometers, really small. So that's interesting. We also have 8 isotopic mixtures, and the ones I'm going to talk about are rubidium-87 with strontium-84. That's a Bose-Bose mixture with which it's very easy for us to make double Bose-Einstein condensates. And we are also using rubidium-87 with the fermionic strontium-87 isotope. And that's very interesting because it has a large interspecies scattering length. And one of the goals since we started on this endeavor was to make rubidium-strontium ground state molecules. And Matthew this morning already introduced the idea here. We want molecules that have both a magnetic dipole moment and an electric dipole moment. And for us, we have 3 valence electrons. 2 form a singlet and 1 is unpaired. So we have 1 Bohr magneton of electronic magnetic moment and an electric dipole moment of 1.5 dBi. And that's very good because we have 2 handles to influence the trap geometry, ultracold chemistry, interactions. So this opens up new and interesting territory for few and many body physics. Now, how do you create ultracold molecules? There are several different ways. You could start with stirrup or photoassociation. You can ramp across magnetic Feshbach resonances. Or we can use trap deformation, for example, confinement-induced resonances. And this is essentially the plan of my talk. We tried all these ways. Initially, we started with stirrup because we have shown that it's really easy to make strontium-2 molecules using stirrup on this narrow 7 kilohertz intercombination line. And initially we thought, oh, this will translate to rubidium-strontium. That's a piece of cake. Let's start this. The problem is, though, that when the rubidium atom approaches strontium, the valence electron of rubidium is magnetic and it really disturbs strontium. So the upper excited state of the stirrup transition is not anymore long-lived and it is becoming much, much harder. Then we looked at magnetic Feshbach resonances, and there actually our problem right now is to create the good starting conditions for magnetoassociation. And finally, we looked at confinement-induced resonances, and that looks promising right now. Okay, let me say a few more words about magnetic Feshbach resonances. So Jeremy's group, first of all, it's not so clear that there are magnetic Feshbach resonances in our mixture because strontium is non-magnetic in the ground state. So the usual coupling mechanisms that you have in alkali mixtures don't exist. But Jeremy's group, they took a close look at the system and they came up with additional coupling mechanisms. And that led us on the exploration search for Feshbach resonances by loss spectroscopy, and we found quite a few of them. And Piotr and Jeremy, you were able to attribute then our loss features to specific coupling mechanisms and resonances in our system. For example, one coupling mechanism is that the valence electron of rubidium couples to the nuclear magnetic moment of strontium, if there is a nuclear magnetic moment, which is only the case in strontium-87. Or squishes the electron distribution around and changes the hyperfine splitting of rubidium. And then there are higher order terms, anisotropic hyperfine interactions. Now, all these resonances, they are quite narrow, as Matthew explained already, even narrow, like milligauss level narrow, and the good ones are only at high fields above 500 Gauss. What this Feshbach resonance study gave us, in addition to the resonance positions and so on, is knowledge about all the interspecies scattering lengths in this mixture, because we know now all the weakly bound states. And here we can make a table of all possibilities, the 4 strontium isotopes, the 2 rubidium isotopes, all the interspecies scattering resonances, and also below here the strontium intraspecies resonances. And I marked here in which field range we find magnetic Feshbach resonances. Now, which isotopic mixture should we choose? Let's first exclude strontium-88 because it's really hard to make a Bose-Einstein condensate here with a -1 Bohr scattering length. Taking a look at the other interspecies scattering lengths, strontium-87, rubidium-87 has a very large scattering length, and indeed we try to make this mixture, but we can't evaporatively cool below a 3 microkelvin because 3-body recombination kicks in and this mixture just burns away. And so we initially thought, nah, let's don't use this one. The nicest mixture experimentally is strontium-84, rubidium-87, because it's really a piece of cake to make a double Bose-Einstein condensate. And to enhance our chance of making use of these super weak magnetic Feshbach resonances, we load our mixture into a 3D optical lattice, and our intention was to create lots of lattice sites with 1 atom on each of each species, and then use magnetoassociation. However, we found out that it's really not trivial at all to create this initial state, and it's very easy you get phase separation between rubidium and strontium, and this approach is really hard. So back to the drawing board. Now we can choose any other one of these interspecies mixtures, and it was Prem here, who is in the audience, a PhD student on the project, who pushed very much on trying to go to this 87-87 mixture, despite its humongous background scattering length. Why is this? I mean, it's an interesting mixture, and perhaps you can find ways to circumvent this problem of 3-body recombination. So why is this mixture interesting? First of all, in this situation here, this is 532 nanometer lattice, where the atoms are really super duper close to each other, the Wannier functions can, describing an atom on a certain lattice site, can reach into the neighboring lattice site. And if your background scattering length is huge, you get very significant interactions between atoms on neighboring sites. So that's kind of interesting. Another reason is that this large scattering length that obviously comes from a weakly bound state. And if you have such a state, then the scattering wave function gets amplified at close range. So here, I plot the scattering wave function in the Bose-Bose mixture, and you see barely any probability amplitude at close range. But if you have this strong scattering length, the scattering wave function is shifted, of course, and it has time to accumulate amplitude when going to close range, and you get this amplification here, which means that all Frank-Condon overlaps with molecular states have a chance of being significantly amplified. So all the coupling between atom pairs and molecules is better. In addition, if the molecular state to which you want to couple happens to be the weakly bound state, then it's even better, because also this weakly bound state is, of course, much bigger than the usual few 10 megahertz bound molecular states. But So all this improved frank quantum overlap that helps you for all methods. So here, our stirrup first leg is quite weak in the usual Bose-Bose mixture. That should be now much stronger, perhaps strong enough to overcome this loss. The Feshbach resonances, of course, are broader, so perhaps it will work. And finally, the existence of this very weakly bound state, for us it's just 14 kilohertz roughly bound, gives rise to the possibility to use confinement-induced resonances. I'll talk about it. But, of course, we are not able to create a quantum gas mixture of this type because of the three-body recombination. So how do we overcome this? So Prem and us, we designed a battle plan. We make separate quantum gases in spatially different locations of rubidium, and then we load the rubidium into a 3D optical lattice, make a Mott insulator with n equals 1 atom per side. Then we make a spin polarized Fermi gas at a different location and move the fermions on top of the bosons. That should work nicely because, you know, the lattice at 1064 nanometer, it's 1/3 as deep for strontium, so you can move it in. And since it's a spin polarized Fermi gas, two fermions can't be close to each other, and of course, then you can only have two atoms encountering each other always. So three-body should be suppressed. And then we ramp up the lattice, get a Mott and band insulator, and we are good to go. So Prem built this system here. It has two dipole traps, a fixed one on top into which we load rubidium, and actually also a little bit of strontium-88, which we use as a coolant for our rubidium. And into the lower dipole trap we load strontium-87, just a spin mixture, 10 different internal states. And we have a connecting dimple to increase the density and then perform evaporative cooling. Now we have a BEC here and a very cold gas cloud down here, and we can move it upwards. And before merging, in our original battle plan would ramp on this 3D optical lattice. And on our way to building this, Prem just put in one lattice axis and ramped up that one lattice. And then you can easily, of course, move your strontium in from the side. Naja, good. If you, here's a little movie showing this just with strontium-88 as a demonstration. So nice, it works. Of course, if you just throw the two gas clouds together without any lattice, no protection, no Mott insulator, we have three-body loss, and we can see a lot of heating, yeah? But then we had a little surprise. If we ramp up our lattice more and more, the heating was essentially absent on relevant timescales. So this is really, really good news. Here you see the temperature of the gas cloud reached after 220 millisecond hold time. If the lattice is just deep enough, there's no appreciable heating. And then only, of course, the normal three-body losses and heating kicks in. And later, we found out that this was actually predicted like 23 years ago in a paper by Petrov, Holzmann, and Schlapnikov, and it has been described in other theory papers in the meantime as well. Good. Now, of course, this absence of heating could be just phase separation. Perhaps rubidium and strontium don't see each other. Could be. To exclude that, we selectively heated rubidium. We can easily do this because the lattice trap oscillation frequency is vastly different for the two species. So we briefly modulate the lattice at the frequency of rubidium, heat it up, and then we just wait, and we observe that strontium also heats up slowly by thermalizing with rubidium. So that tells us these two gas clouds are in contact. And indeed, we can even evaporatively cool these two gas clouds now to even lower temperatures than before. So that's all nice. This is a key message of my talk here, yeah? In a deep 1D lattice, strontium and rubidium mixtures are protected from three-body recombination. And that's great now as a starting point. We don't even have to bother putting the other two lattice schemes in. Let's go with that already. Now, I spoke about this and magneto association still didn't work when we tried, so, but okay, perhaps in a 3D lattice it would. But there is this other method of using confinement-induced resonances to get your molecules. So how does this work? Let's take a look. We have two atoms in this trap, and you could describe it as coordinate of atom 1 and coordinate of atom 2, but you can also change coordinate system and describe it as relative coordinates and center of mass coordinates, yes? And so center of mass coordinates here, at very close range, you have, of course, the molecular potential, and then here we have the trap, and this is just the center of mass motion. And let's assume we have really cold gas clouds, then our atom pairs are just in the lowest state of our trap. And I plot here energy over trap depths, these various states which you have here. So the initial state is just this here, both atoms in the ground state of the trap. Of course, it goes up with 2 times 1/2 h bar omega when we ramp up the trap. Yeah, good. We also have this molecular bound state, just 14 kilohertz below here. And we have to think also of excited center of mass motion. So let me first plot the excited center of mass motion here, 1/2 h bar omega for each atom going up, and then just below it, the molecular state. And you see the atom pair state and the molecular state in the excited center of mass level, they cross. I mean, you see here energy conservation. And the atom pair in the relative motion can go from this lowest trap state to the molecular state that liberates about 14 kilohertz energy. And that energy then goes into some excitation of the center of mass motion. And that's only possible because the state is so weakly bound that it's comparable to the trap harmonic oscillator spacing. Okay, but like this, of course, it's just like 2 levels crossing. There's no avoided crossing yet. And indeed, if you have 2 particles in perfectly harmonic wells with perfectly identical trap frequencies, if you make this change from coordinates, from individual coordinates to center of mass and center of and relative motion, you just end up with perfect harmonic oscillator states, and there is no off-diagonal element in your Hamiltonian whatsoever, no third term in your Hamiltonian. However, if you break my conditions, be unharmonic or have different trap oscillation frequencies, then you do get additional terms, correction terms, in your rewritten Hamiltonian in the relative motion versus center of mass terms. You get terms which contain products of the relative motion coordinate and the center of mass coordinate. Yeah, so there's a perturbation of diagonal elements in my Hamiltonian, and for us this is very strong because we have a factor 3 difference in our polarizability, in our trap frequencies, the square root of 3 between rubidium and strontium. And we are in a sinusoidal trap, not a harmonic trap at all. So we should have an avoided crossing here, which might be significant. And to get to these molecules, you just have to ramp the trap depth down. Okay, so let's try that. But of course, we have to somehow detect our molecules, yes? So how do we do this? We need to exploit some kind of difference between the molecules and the atoms. And for us, it's the polarizability. So rubidium is much deeper trapped. And strontium, rubidium is just the sum of these 2 potentials, and per atom, it's just the average. And of course, we need to think of gravitational sag. So that's how the blue potential for strontium looks like, and black rubidium. The 2 clouds are separate. Now we merge the 2 clouds. Now what happens if we unmerge, if we just move the lower trap down? You can see rubidium, because it's much better trapped, it's still levitated, whereas strontium gravitationally sags downwards. And at the moment when the traps are split, this wall moves in between rubidium and strontium. And we can do this as often as we want. We barely see any rubidium in the lower trap ever. Now, if we should create rubidium-strontium molecules here by trap lattice ramp down, for example, then if we move the trap down, the rubidium-strontium is also weakly trapped, and if the settings are right, it will sag, it will fall down, yeah? And then we can make absorption images, and if we are lucky, rubidium-strontium excited state molecules, they sometimes pop apart into a rubidium atom and a strontium atom, then we just have a cycling transition, and we see it. So our signal is any rubidium in the lower trap. And that's the outcome of the experiment. So here we perform an adiabatic ramp down of our lattice, and this is the final lattice well depth. And here the rubidium fraction in the lower trap. You see here, if we stop early, there's barely any rubidium down here. But if you ramp lower and lower, hey, the rubidium shoots up. Of course, this could have many explanations. For example, the lattice also keeps the gas cloud a little bit up. But then you make cross tests. For example, if you put no strontium in your system whatsoever, there's never any rubidium pull to the lower trap. If we suddenly switch the lattice off instead of making an adiabatic ramp, there's never any rubidium over there. And if we ramp the lattice adiabatically down and then adiabatically back up, our signal disappears as well. So this is all very promising, but this result is 10 days old or so, yeah. And now, of course, we want to poke it and make sanity checks and so on. So we made a few more checks. For example, we have magnetic Feshbach resonance predicted between the molecular state of interest and the atom pair state. And we think that we saw, when we put the magnetic field just there, that it enhances our signal. But that's data from like last Saturday or so. So we have to take this again to be sure. Also, another test is you just jump onto the avoided crossing, wait a little bit, and then you jump to no lattice. And so you build an interferometer, and you should see oscillations. And we did this the first time on Thursday, and then again on Saturday. And it seems to be there, but it's too noisy to present. We have to really, really do this again, but it looks not bad. And now let's assume that this indeed works, and it's not just like Luke said, nature's way of getting us. So then we have this weakly bound molecule. Now comes an intriguing possibility. We know about these weak Feshbach resonances between the scattering state and deeply bound molecular states. And actually, these states, they should dive through our weakly bound molecule. And the same coupling mechanism that gives rise to the weak Feshbach resonances should give rise to avoided crossing here. And that should be bigger, yeah? Because you don't start with a scattering state, you start with a real molecular state. So perhaps by just sweeping across this magnetic field range, we can make a molecule in a 6 gigahertz bound state. And that would be a perfect starting point for deep stir-up. Or if it doesn't work, then we make a first stir-up on the red mode transition to a gigahertz bound state and then stir deep down. Okay, I'm nearly at the end of my time. Let me show you one little nice thing you can also do with mixtures. So we can use rubidium as co-magnetometer, and that enabled us to really nicely nail down the G factor of strontium-87. We have these 10 spin states, and they're roughly 180 Hertz per Gauss per MF states separated. And we just apply magnetic field, super stable, that as Mateusz and Prems work to build very nice magnetic field system. We use rubidium to measure our magnetic field very precisely at the same time as driving this nucleus transition. And then here you see strontium driven away from the initialized polarized state, and we get a very nice measurement to 5 or perhaps even 6 digits of our G factor of strontium, which is better than what was done in hot vapor cells or in ions in liquids. And that is our stepping stone towards using the strontium nuclear spin states as a qubit by applying tensor shifts and then driving these RF transitions, which will be different between these different nuclear spin states. Okay, so this brings me to the summary. I've shown you that rubidium strontium has a long lifetime in the 1D lattice despite this huge scattering length. And perhaps we have seen the formation of weakly bound rubidium strontium molecules. I mean, take this with a grain of salt. We need still to make lots of sanity checks to be absolutely sure that this is true. And we have used rubidium as a co-magnetometer to establish a precise value for the strontium G factor. And yeah, all of this work is of course only possible with great people. So Mateusz, Lukas, and Prem, you worked very hard to get this really good magnetic field control in our lab. And then, okay, the pandemic hit and Prem had to rebuild the whole machine. And then Prem really pushed in going to this strongly interacting mixture and built this whole merger trap system. And it really seems to pay off. I mean, all the results I showed came out the last 6 weeks after a 2-year drought, also triggered by the pandemic. And this stuff is apparently so cool that it even attracted French President Macron and the Dutch king to our lab. Uber had to pay like 200,000 euros to realize this visit. Security and stuff like that. But it was a lot of fun, I can tell you, in a coffee break. And then we have other projects. So we made a continuously existing Bose-Einstein condensate that's the equivalent of a CW optical laser with perfectly reflective cavity mirrors for matter waves. Yeah, and now we are working on making one of these cavity mirrors transparent and outcoupling continuous atom laser beam. We use this continuous supply technology for strontium beams to make super radiant clocks on the millihertz clock line. And within new technology, quantum delta NL program, we built a 0 daytime clock where we move strontium into one of 4 interrogation zones to always have a sample available for phase Korean clock interrogation. And we have individual strontium atoms in tweezer arrays. And yeah, this is all, of course, only possible if you have lots of enthusiastic and bright people doing most of the work here. And if you're interested, yeah, as everyone, we have, of course, PhD and postdoc positions. So thank you very much.
Thank you so much for the great talk and being on time. Great. Any questions? Apparently it was so clear that it's okay. There is a hidden.
So different of the sort of association procedures that you looked at were using different isotopes, and I wasn't quite sure why. So can you talk a little bit about why some of them were 8787, some were 8784?
Yeah, so I mean, these are the 2 main species with which we worked. 84, 87 is just beautiful to make Bose-Einstein condensates with. And that sounds like a natural starting point, and it sounds like you should be able to make a double mode insulator to enhance, to reduce the size of the scattering wave function, enhance the probability at close range, and make use of these super narrow milligauss wide Feshbach resonances. But we are not blocked by the Feshbach resonances themselves. We were blocked by the ability of making nice double mode insulators. So there is still a chance of using magneto-association. And then we switched tack and went to the strongly interacting species simply because it enhances our scattering wave function at close range. So all the Frank-Compton overlaps with molecules become much stronger. Yeah, and that will apply for all methods, but the first we tried, I mean, you probably briefly tried magneto-association. Oh, yeah, didn't immediately work, but yeah, it's a pancake situation, not a 3D lattice. But the confinement-induced association, that might have just worked. We will see.
Any more questions? Oh, here.
What's the physics underlying the stabilization of the mixture in one deconfinement?
So to my understanding, you get a much worse overlap between the scattering state of 3 atoms in 2D with the state that you need to form a molecule and an atom flying away, so 3-body scattering lag.
So it's not that it's pushing the bound state above threshold?
Not to my understanding. It's a Frank-Compton kind of argument.
Before Caden's question, can I just ask Gabriel to start setting up and then Caden? No? Oh, sorry. Okay, great. Then any more question? Okay, then one more question maybe. Can you give me like intuition behind this suppression of 3-body recombination with this deep lattice, like intuitive picture? Why?
Yeah, that's a bit what I told Jeremy. I mean, it's just the the overlap of the initial scattering wave function with the 3-body state gets worse in this strongly confined direction.
Okay.
So, I mean, yeah. In Jora's paper, he writes it up. He splits the wave function in the axial and radial part, and then he introduces some eta aspect ratio parameter, and he writes it suppressed by eta to the power of 6 because of wave function overlap.
Thank you. Okay, then let's thank the speaker.